Okay. So let us start with a recap of previous lecture. So in the previous lecture, we started with the definition of graphs, and then we saw that graphs can be represented as a diagram, and then we studied different types of graphs like simple graphs, multiple graphs, right, multi-graphs, graphs with loops, without loops. And then we went on to see what is a degree. Then we learned the first theorem of graph theory. Right? And after this, we looked at special graph families like complete graphs, bipartite graphs, etc. And then we looked at paths and then connectedness. So these are the main things that we discussed in the previous lecture. So let us continue. So here I define what is called adjacency matrix of a graph. So the graphs have different types of matrix representations. So we will discuss one of them in today's lecture, and then maybe some other representations can be introduced later in the course. So what is the adjacency matrix? So adjacency matrix is basically a matrix which represents or gives the full information about the graph by way of a matrix. So this can be useful to give us input to to computers, right? For example, represent this or study even you can study the properties of this matrix to study the properties of graphs, several properties of graphs. Now, so how do we define this adjacency matrix? So we have the rows and columns of this matrix indexed by the vertices themselves. So if there is n vertices in the graph, then we have n rows and n columns. So it's going to be a square matrix where the ijth entry of the matrix will be 1 if there is an edge from the vertex I to vertex j, right? The ith vertex to the jth vertex. So if u and v are the vertices, the corresponding columns, the uth row and columns and rows, right? Uth row and vth column. If you take, then uv entry will be 1 if uv is an edge, and otherwise it will be 0. This is for our simple graphs. If you allow multiple graphs, we can set the aij, the entry, to be the number of edges between the pairs. Okay, so that for us at the moment it's not important, but one can do that. Now, if the graph is loopless, then you know that the diagonal entries are going to be all zeros. And one can also see for our undirected graphs, the simple graphs, the matrix is going to be symmetric. Okay, these things one can easily verify. So here is an example of the graph, right? You have this graph like 1, 2, 3, 4, 5 vertices, and the edges are given as in the figure. So 1, 2 is 1, 2 is an edge. So therefore, the entry 1, comma 2 in the matrix is going to be a 1. And because 2, 1 is also an edge, you will have both of these entries to be 1, right? Similarly, you can fill up 2, 4 is going to be there for 2, right? 5, 4, 4, 5, 3, 4, 4, 3, and 2, 3, and 3, 2, right? So all these entries will be 1. Every other entry is going to be 0. So this is how we define the adjacency matrix. Okay. Now, it would be instructive to basically look at some examples of this and then study some properties. For example, what can you tell about if you look at the square of the matrix, right? The adjacency matrix. So can you think of what it means to look at the square of a matrix? And the entries, like what will be entries of this matrix represent something like that. So think about this. We will discuss this in a later class or as part of some assignment questions. So just think about this for the time being. Now, in the previous class, I did not give you any homework questions. So let me now give you a couple of questions that you can think about. So here is a question. Prove that in any graph, the number of vertices whose degree is an odd number is always even. Okay. So the odd degree vertices will be always even in a graph. Then the second question is to prove that every graph contains two vertices of the same degree. Okay. Then the third question asks that given a bipartite graph gxy with a bipartition x and y, and we assume that there are no isolated vertices. Okay. Suppose the degree of every vertex in x, degree of x is greater than or equal to degree of y for every edge xy where x is in the set x, right, the partite set x, and y is in the partite set y. So you have this graph where the edges are from the set x to set y, and if you take any edge, the degree in x will be greater than or equal to corresponding endpoint in y. Now, in this case, the claim is that the cardinality of x is less than or equal to cardinality of y, with equality if and only if for every edge degree of x is equal to degree of y. Okay. So this is something you can try to. Then we studied independent sets. So here is an example. Here is a question to find the largest independent set in these two graphs, graph A and graph B. So give an example of, so you can label the vertices first and then list out the vertices, or you can just mark them, right? Draw the graph and then mark the set and then show that this is actually the maximum. There is no larger set is possible. So this will be more challenging to do. Okay. So not just to find a largest one, but also try to show why it is the largest one. The fifth question is to check whether the given graphs are bipartite. So the graph A is given here in the picture. Graph B is given as another picture, and graph C is also given. So check each of these graphs and show if which of them are bipartite and why. And if it is not, then why not? If it is yes, then why? And if it is yes, give a bipartition. If it is not bipartite, then give a reason why it is not bipartite. Okay. Now, we define, this is a natural way of looking at graphs, right? The isomorphism between graphs is basically a bijection, right? Which maps the vertices to vertices such that the edges are preserved. Okay? So we are looking for a bijection, from the vertex set of the first graph G, let's say, to the graph H, vertex set of H, such that the edge UV, right, belongs to edge set of G for U and V in the vertex set of G, right? Of course, if and only if the corresponding images f of U and f of V, they form an edge in the graph H. And this is like bidirectional, right? So like if there is an edge here, there is an edge there, and there is an edge here only if there is an edge in the graph G, right? So it's if and only if. Now we say that G is isomorphic to H if we can find such a function, and we write G, with this symbol G isomorphic to H. Okay, so this kind of a map is isomorphism, and isomorphism is basically defines a binary relation on the graphs, right? And it one can show that it's an equivalence relation. I will give it as an assignment question for you to work out that the isomorphism is an equivalence relation on the graphs. So here are a couple of examples. So the first graph I have given here, it's 1, 2, 3, 4. which is represented as just a figure, inverted n, right? And this is isomorphic to the graph on the right side. One can immediately see this, right? Once you see that this is actually isomorphic to a path graph, right? P4, right? You remember the path graphs, and P4 is a path graph. So because it is isomorphic to P4, both of them are isomorphic to P4, and then we see that it does not matter what is the representation, right? Only that such a function exists. So you can find such a function, and I think I will leave it as I will leave it you to work out the details. Now the second one may be a little more challenging to find an isomorphism. So what you can do is to take this graph and try to label them, and use the label to find an isomorphism, right? So just give labels to both and then try to find. But even that may not be immediate. So one thing you can try to do is, can you try to find a way to define these graphs in a set theoretic fashion, right? So I will give you a hint. Like there are 10 vertices, okay, and the 2-element subsets of a 5-element set will help you to define this graph, right, on the left hand side, and then you will be able to use it to see if you can find an isomorphism or not. Now, a subgraph of a graph, right, is basically a graph whose vertex set is a subset of G, and the edge set is also a subset of G. Okay, so a subgraph is basically a graph where the vertex set is a subset of G and edge set is a subset of G. Now, one should keep in mind that just V of S subset of V of G and E of S subset of V of G is not necessary to make sure that the graph is a subgraph. I mean, to make sure that what you get is a subgraph or not, right? So if you look at the set theory definition, it will be clear. But I will try to frame it as a question later. But try to see if you can find some example of a graph, right, with some subsets of vertices and edges given, which is not really a subgraph. Okay, so try to find something like that. Now here are some examples of subgraph. So given a graph on the left side, right, with the yellow vertices. On the right hand side, I have given several subgraphs of this graph. Okay, so H1 is basically a 4 cycle. You can see it's a 4 cycle, right? 1, 2, 3, 4, and this is is a subgraph, right? You can see that all these vertices are present in G, and all these edges are also present in G, right? So therefore, you see that it's basically a subgraph. Right? And then and S2 is a graph, right, where you again see that these are all subgraphs of G. Right? Then S3, S4. So all these 4 subgraphs are there. H1 and S4 are both 4 cycles, but they are coming from different cycles in the graph G. Now, if you look at these graphs, you can see that there is actually a difference, right, uh, in some properties. Okay, so one of the properties is that, like in if you look at this graph S2, right, if you look at the graph S2, look at all the vertices of S2, right? So all the vertices of S2 are of course present in G, but whenever there is an edge in G between the corresponding vertices in S2, there is that edge is also present in S2, right? So therefore, S2 is said to be what is called an induced subgraph, right? So an induced subgraph is basically a subgraph where you have a subset of vertices, and every edge in the original graph, right, let's say G, which is present between these pairs of vertices in this subset, is also present in the graph. So in that case, it's called an induced subgraph. So in other words, induced subgraph is the largest subgraph on that subset of vertices, right, that you can find. So here is the definition of induced subgraph. Let G be a subgraph. Let G be a graph, and let us say that S is a subset of the vertices. Then the graph, H, which is obtained by the induced, obtained as an induced subgraph on the vertex at S, is defined as follows: that for every UV in the in the set S, in the subset, UV belongs to the edge set of H if and only if UV belongs to the edge set of G, right? So whenever the edge is present in G, it is there in H also, right? So this is the induced subgraph. So you can see that which are the induced subgraphs here. For example, H4 is an induced subgraph and S2 is an induced subgraph, right? On the other hand, H1 and S3 are not induced subgraphs because I have all the vertices in S3, but some edges are missing. Similarly, 1, 2, 3, 4 is missing, but 1, 3 edges missing in S1. On the other hand, H4 is an induced subgraph because the vertex 3 is not present. So the edges connecting to 3 cannot be, of course, present in H4. Right? So therefore, H4 is an induced subgraph while H1 and S3 are not. S2 is also induced. Again, yeah, so I think I have given the examples here, right? Like you have the graph G, and then H1 is an induced subgraph here in this case. S2 is not an induced subgraph because the vertex 5 is included, but the edges are not all in there. S3 is an induced subgraph here, and H4 is not. Okay, now by decomposition of a graph, what we mean is to write this graph as a union of edge disjoint subgraphs. Okay, so the vertices need not be disjoint, of course. Right? So you are basically finding subgraphs where the edges appear only once, right? In this list. So you have a list of subgraphs such that each edge appears exactly once. Then it is called a decomposition. Of course, one can ask a decomposition to be, try to be the same copies of the same graph, or it can be arbitrary set of graphs. Each one is basically a decomposition, but you can ask, some specific types of decomposition. For example, here you have the complete graph K5 listed here, right? And I have given a decomposition into two copies of the cycle on 5 vertices, right? Because if you look at the outer edges, the yellow edges, they form a cycle, right? They form a cycle which is a C5, right? 5 cycle. And if you look at the internal vertices, internal edges, the blue edges, they are actually forming a cycle, right? So I start from any vertex. It is basically a cycle. Right? So K5 then decomposes into two copies of C5. What about other examples? So here is another example of K4. K4 is decomposed into several ways, right? So for example, I decompose K4 into two copies of path on forwards, right? So the blue edges and the yellow edges, right? So this we have seen earlier that they are basically isomorphic to P4. Then I have decomposed K4 into three copies of P3, right? In the bottom. So here you have the three different colored P3s, right? P3 is a path on three vertices, not three edges, right? So yeah, I have 3 copies of P3. And then another way to decompose it to P2 plus P3 plus C3, right? So you have the blue C3, then you have the uh, yellow orangish P2, and then you have the reddish P3, right? So they have these 3 different ways of decomposing. There could be several more one can think about, but this is what is meant by decomposition of a graph. Now, this decomposition can be quite challenging in some cases, right? Now, one thing that you can try to think of is, can you find out? This is one of the classic questions in design theory, right? Can you try to think of when is it possible to decompose, let's say, the complete graph on let's say n vertices to copies of 3 cycles of triangles, right? So a triangle is basically the complete graph on 3 vertices or cycle on 3 vertices, right? Something like this. This is the triangle, right? So, think of when you will be able to decompose a complete graph uh, into copies of triangles. At which point the necessary condition, right? Sufficiency, you can try, but at least try to find the necessary condition. Now, here I give an example how to decompose K7 into copies of triangles. Okay, so let us see how to decompose complete graph on 7 vertices to copies of triangles. Let me just list the vertices first. Okay, then we will see how to decompose it into triangles. Okay, so let us just take some triangle first. Okay. Then I will look at another triangle, and then another triangle. Right. So these are adjoint triangles. So I have done one decomposition, right? I mean, not decomposition. I have done with this one vertex. All I can do. Then I will look at other vertices, right? So let's say that this vertex I want to now decompose. Let me see if it is possible to do. Okay, so I can do this maybe, right? So this is one. Then I can also do this. No, I cannot do that. Yeah, I can do this. Right, so I have 2 copies of the white triangles, 2 white triangles. Is there any other triangle I can see? Okay, let me see this. Right. Now, if you look at any other triangles remaining, you will see there is one more. Let's say it's blue here, right? This one. So with this, how many triangles I have? I have 3 plus 2 white, 5 plus 6 and 7, right? 7 triangles. So 7 into 3, 21. And for the complete graph, how many edges I have? I have 7 vertices, and therefore 7 into 6 by 2, which is equal to 21, right? It's 21 edges. So I have covered all the 21 edges, right? And you can see that, like, every vertex has the maximum degree, which is 6. And we have actually given a decomposition into 7 triangles. So K7 can be decomposed into copies of triangles. So this way, one can ask such questions, and this could be of very high interest, because many times such questions crop up, and that is why the design theory is a separate branch of combinatorics, and dealing with such questions. Okay, now a few more questions for you, homework questions. So first, prove that Isomorphism is an equivalence relation on the set of simple graphs. Okay. So this one we mentioned earlier. Then the second question is to check for the isomorphism among the set of graphs given below. So we have this 1, 2, 3, 4 graphs given, and find which pairs are isomorphic, etc. The third question is to find all automorphisms. So what is an automorphism? An automorphism is an isomorphism from a graph to itself. Okay, so find all the automorphisms of the following graphs. So one is to find the automorphisms of P4, which is the path on 4 vertices. Then the C4, the graph cycle on 4 vertices. Find all the automorphisms, and find for K13, which is this graph with which is a complete bipartite graph, right? With one vertex on one side and 3 vertices on the other side. Okay, and then the fourth question is to decompose the graph to copies of K13 and copies of P4. Okay, so decompose this following graph. Right. So this graph is called the cube. We will see why it's called the cube, and decompose it into copies of the graph that we just saw before, right? K13, this one, and copies of P4. And the fifth question is let G be a simple graph in which every vertex has degree 3. Okay, so all the vertices have degree the same, then the graph is called a regular graph. We will mention that later. Then prove that G can be decomposed into copies of K13 if and only if G is bipartite. So if the graph is 3 regular, right, has all the vertices have the degree 3, then one can find a decomposition into K13, right, complete bipartite graph K13, if and only if the graph is bipartite. Okay? So prove this statement. And with that, we continue to more topics. Okay. So walks, trails, and paths. So a walk in a graph is is basically right traversing the graph in through its edges, right, starting from some vertex, right. Let us say that one decides to go like this, right, 1 to 3, let's say 3 to 4, then he decides, okay, let me go back to 3, right, and then maybe go back to 4, right, then go to maybe 2, right, go to 5, and stop. Then one can think of other walks, right? Like for example, one might say that, okay, I go from 1 to 2, 2 to 5, 5 to 8, and stop. Maybe like one decides to go from 1 to 3, 3 to 4, 4 to 2, and 2 to 1. Or go from 9 to 10, right? 10 to 13, 13 back to 10, go to 8, 9, and then back to 10. I mean, yeah. So this way, a walk is basically a sequence of vertices such that the consecutive pairs form an edge in the graph. That's all, right? You can go in whichever direction you want. As far as every vi plus 1 is an edge, for the high ranging from let's say 0 to k minus 1, right? So basically a sequence starting from a vertex, let's say u, right, ending in a vertex v, and we don't put any restriction on whether the vertices can be repeated or anything, right? As far as there is an edge from vi to vi plus 1, we are allowed to take that. And any such sequence is called a walk. So a uv walk is basically starting from the vertex u and ending in the vertex v and satisfying this condition, right? And it has length k if the number of edges in this walk is k, right? Now if you have any walk like this, right, as I told you, like you may be allowed to repeat vertices. You can also repeat the starting vertex. So u can be equal to v. So this is also allowed. So if u is equal to v, then we call the walk as a closed walk. Otherwise, it is an open walk. So if w is a uv walk in which u is equal to v, then w is said to be a closed walk. And if not, then we say the walk is open. Now we said that we are allowed to repeat vertices and edges in the walks, right? Now suppose I say that okay, maybe you can uh, repeat the vertices, but you don't want to repeat the edges, right? You remember the Königsberg bridge problem when we converted into the graph question. We said that we don't want to trace over the edges, right? More than once, right? So you don't want to trace over the edges again. So we can only go through each edge once, right? Now, so to represent something like that, one can say a trail is basically a walk, but edges are not repeated. But I am allowed to repeat the vertices. So such walks are called trails. So examples of trails, for example, in this graph below, let me say, okay, I go from here to here, right, like this, then maybe like this, like this, like this, like this, like this, right, like this, and like this. This is a trail, right? So we have a trail, where I have repeated vertices and I have not repeated edges, right? I mean, now the question is that, like, in this graph, for example, can you cover all the edges and visit exactly once and come back to the starting place, right? Is it possible? For example, let me show you if I can do that, right? I go from here to here, right? Then what I do is that I go here, 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 and here. Then I take this, 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 and finally reach here. So basically, I took all the edges, right? I went through all the edges without repeating the edges, and I covered all the edges and came back to the starting place. So it is possible in this particular graph, right? Then one can ask, is it possible in every graph, right? So maybe you can try if it is possible in the graph on the right hand side. I will show you that I can go from, let's say, one vertex, right, like this, and go through every edge exactly once, but I did not come back to the starting place, right? But now you can think of, is it possible to do that? And if it is possible, then how to do it? And if it is not possible, why? Right? So think of this. So a trail that visits every edge of a graph is called an Eulerian trail, right? Or an Eulerian path. Because as you remember, the graph theory itself was discovered when Euler tried to think about this kind of questions, and therefore it's called Eulerian trail, right? and a closed trail like that. The question in the Königsberg bridge problem actually asked to find a closed trail. So a closed trail that visits every edge is called an Eulerian circuit or an Eulerian tool. So the question is that whether the graph in the Königsberg bridge problem have an Eulerian circuit or even an Eulerian trail, right? So the question was initially about Eulerian circuit, but even if you can find an Eulerian trail, that is also fine. Okay. So the Eulerian trail may be closed or not. If it is closed, it is Eulerian circuit. If it is not, it's Eulerian, just open Eulerian trail or Eulerian path. Now you can also think about when does a graph actually admit an Eulerian tool, right? So what condition you can impose on the graph such that you can say that okay, these graphs definitely have an Eulerian tool and this graph does not have, something like that. Now we had defined walks and trails. Now we can define a path. So a path is a graph, path in a graph. So we define a path graph, right? So here, the path is basically defined as a subgraph, and of course, what we want is that the subgraph is going to be isomorphic to one of the path graphs, right? So a path in a graph is a walk such that no vertex is repeated. So a walk is defined as just a sequence of vertices where every consecutive pair is sitting as an edge, right? Then here we are saying that okay, a path is a walk where no vertex is repeated. So if vertex is not repeated, of course, edges cannot be repeated, right? So it is basically also a trail in which no vertex is repeated, right? So a path is a walk where no vertex is repeated. So let us look at an example, right? So this is a path, right? So you start from this vertex and you say 1, 2, 3, 4, 5. Right? Now, what I have drawn here is basically a path, right? 1, 2, 3, 4, 5 is a path. Right? And you can see that this subgraph, right? It's a subgraph, right? It's a subgraph which is also isomorphic to the path on 5 at P5. Now, and this is a walk because it's just a sequence of vertices where the consecutive vertices are adjacent. Right? We defined a path earlier as a sequence, a graph where you can order the vertices in a sequence where the adjacency is precisely when the consecutive vertices are adjacent, right? And here you can see that is how we define the path, right? So you take the sequences that the consecutive vertices are adjacent, you don't repeat vertices, and then what you get is a path. Now, a path as a subgraph is basically isomorphic to the path graph, as we mentioned before, Pn for some natural number n, right? And you can look at other examples in this graph itself, right? So, for example, 1 to 13 to 12, and going to 2, then to 3, then to 10, 9, 8, 7, 6, 5, 4, right? This itself is this is also a path. Now, the paths in the graph can be used to define distance, in graphs. Okay, so one can define distances. There is also the version of weighted distance and there is the unweighted. So we are looking at unweighted graphs at the moment, and the distance in an unweighted graph is basically the length of the shortest path connecting a pair of vertices. Okay, so if u and v are vertices, then look at the minimum length path that connects U to V, right? And its length is called the distance of the distance between U and V. Right? Now, if there is no such path, right? If two vertices are in different components, right? Then the distance is as defined to be infinity. Now, yeah, so just to look at some example, maybe, right? If you look at this graph, right, the distance between, let's say, so the distance between 1 and 3 is 2, right? Because you have several paths from 1 to 2. For example, 1, 2, 3 is a path. 1, 2, 4, 3, not 4, like U3 is a path. Then 1 to this vertex is this, and this is a path, right? And among all these paths, the one with the smallest number of edges is 2, right? I mean, like the is 1 to 2 and 2 to 3. So the length of this path is 2, and that is therefore the distance between 1 and 3 is 2. On the other hand, distance between 1 and 2 is just 1, right? And what is the distance between U and V? There are several UV paths. Again, U to 6 and this vertex 5 and V. Right? Then U3 for V. And this U3 for V seems to be the smallest one can show that. And therefore, the shortest, the distance between U and V is 3. Right? There are 4 vertices, but 3 edges. Now, this proposition says that if G is a graph and P is a minimum length UV path, then P is an induced subgraph of G, right? So this path, we said every path in a graph is basically a subgraph. Now, we claim that if you are talking about the minimum length path, then it must be an induced subgraph. Okay? So just look at this and try to prove it yourself. Okay? So, for example, here U and V, right? So U, then this vertex and V is the shortest path, and one can verify that it is an induced path. On the other hand, not all induced paths need to be shortest, right? For example, I can go from here to here. No. I can go from here to here, right? Here, here, then here, and here. This is also a UV path, which is also an induced path. But this path is not a shortest path, right? Similarly, like this path, right? U to V path, U to 3, that path is not an induced path, right? I mean, because the 2 to U edge is not included in that path. But that is coming as an induced subgraph when you take the vertices, all these vertices in the path. So therefore, you have these paths which are induced and not necessarily not induced. So, but when you are talking about the minimum length path, then it must be an induced subgraph. Okay. So let me wind up, and we will continue in the next lecture with more topics.